Happy Pi Day, fellow programmers, or whoever else stumbles upon this video. Yes, it's this time of the year again. It's Pi Day, the 14th of March, and in this video I want to present my Pi Day contribution for this year, show you the maths behind it and tell you how I made it. You can find the link to the GitHub repo in the description, and I put timestamps there if you want to skip certain parts of this video. So, without further ado, let's start with the maths. The Monte Carlo method. What is it? Let's imagine you are playing darts on a darts board which has an outer bounding square. So let's throw 3 darts on this darts board. 1, 2, 3. As we can see, we have 2 in the circle and 3 in total. What if we would throw not 3 darts but an infinite amount of darts? As we can see now, the whole circle is filled and also the whole square is filled. So what would we do to generalize the amount of darts in the circle? We could just use the formula of the area of the circle, which is pi r squared. And how do we get the total amount of points? We can use the same logic as for the circle, so we can just use the formula for the area of a square, which is just a squared, where a is the length. But in this case that would be 2r squared, as we have the circle with the radius r, and we have the side length of the bounding square is 2r, so we have 2r squared, which would be 4r squared. If we would now calculate the ratio between the darts in the circle and between the darts in the square, we would get pi r squared divided by 4r squared. The r squares cancel out and we get pi divided by 4. Now we could rearrange this formula so that pi is isolated on the one side. So just multiplying by 4 and we get pi is equal to ratio times 4. Back to our previous example with the 3 points, we could just use this formula now. 2 points in the circle divided by 3 points in total times 4 is equal to 3, which is a good approximation for pi, and that's the Monte Carlo method, a geometrical way to approximate the value of pi. So if you understood this, we can easily bring this thing into 3 dimensions. We just say we have a cube, and inside of this cube we have a sphere. So now we can take the volume of a sphere, which is 4 over 3 times pi r to the third, and the volume of a cube, which is in this case 2r and this to the third, which is in this case 8r to the third. So if we now calculate the ratio, and we get pi over 6. We can now test this if it works with taking some random points, and as you can see we have 4 points in total and 2 points in the sphere, times 6 is equal to 3. Which is again a fine approximation for pi. So now that we understood how this method works in theory, I want to create a program which visualizes this process. For that I created the SM3D-WF-RPG, which stands for Super Minimal 3D Wireframe Renderer in Pygame. This overcomplicated name summarizes perfectly what this renderer is capable of. It can render single points, such as the 2 primitive objects, the sphere and cube. It can also rotate these to increase the perception of 3D space on a 2D screen. But how does such a renderer actually work? Well, for a projection of a 3D point to the 2D screen, we need to understand the concept of vector by matrix multiplication. What do I mean by that? So, we have a vector, and we have a matrix, which is in this case 3 by 3, which looks like this. So how do we multiply this vector A times the matrix M? Well, you basically have to multiply every column by every row of the matrix. So let's do that. So we have AX times M11 plus AY times M21 plus AZ times M31. And let's do that for the next row, which will be just again AX times, this time the second row, M12 plus AY times M22 plus AZ times M33. And that's it. That's how you multiply a vector by a matrix. The important thing is that the matrix has the same amount of columns as the vector rows has. So this one would be 1, 2, 3 rows, and this one would be 1, 2, 3 columns. So now let's try to project a 3D vector to the 2D screen using the projection matrix. Here we have again our vector A, this time with x, y, z, and this is the projection matrix. This maybe looks very complicated. I will not explain why it is like this. I can just tell you what these certain variables in there mean. So basically we have height divided by width, which is just the aspect ratio of your screen. We have a screen, and then we have our height and our width, and we're dividing this so that we get the aspect ratio. And then we have over here the FUV. What this means is basically the angle the 3D camera is seeing all the objects. So let's try to multiply our vector by this matrix. And that's how it looks multiplied. And we can basically remove these because they are just 0. But wait, now we have 3 components, but we want 2 because we have a 2D screen. Let's just divide the x and y values by the z value. And there we go. This is our projected point A, displayed as a vector B. Looks very complicated, but when you wrote it down once in code, you never have to touch it again. But what if we want to rotate the point before we actually project it? Well, you just learned about multiplying a vector by a matrix, so understanding this should be very easy. You basically have your vector A again, and this time we have a projection matrix. I'm going to use the matrix for rotating about the y-axis. That's just the one which I used in my code, but you can find other matrices for the x rotation and the z rotation on the Wikipedia page. And this is it. The rotation matrix to rotate a point around the y-axis. And if we would now multiply the A vector by this matrix, we have our rotated point. And these are the basics of my 3D renderer. Putting this theory into code was actually much harder than I thought it would be. Here you can see some of my failed attempts, but in the end I actually was able to make it. And then I just created the logic with the points, which is actually pretty easy. Changing the colors based on if it's in the sphere or not, and adding some text based on the formula we just discussed some minutes ago, and it's done. My Pi Day contribution for this year, and I think it's great. Tell me in the comments what you think, and see you next time.